I'm Chanhyeong from Chung-Ang University. Today, I'll talk about ScaleSwap. ScaleSwap is a scalable swap system designed to use all-flash swap arrays efficiently. This work is a collaboration with Taehwan and Sangjin from Chung-Ang University and my advisor Yongseok. First, let me explain the motivation. Today, many workloads need a lot of memory like machine learning, big data, graph processing. But DRAM is expensive and it is hard to scale DRAM to very large sizes. So the total cost becomes high. At the same time, NVMe SSDs are much faster now. So we can use SSDs as swap space to extend memory, especially when we have multiple SSDs. However, the default Linux swap has a big problem. It does not scale well when we use many CPU cores and many SSDs. Even with multiple SSDs, Linux swap still has many shared locks. So many cores spend time waiting instead of doing real work. That's why SSD performance can scale, but Linux swap throughput stays almost flat, around 4 gigabytes per second. So our main issue is the swap design in the OS. Before our design, let me quickly review Linux page eviction. Linux uses RLU lists to choose pages to evict. There are two lists, active and inactive. Active pages are hot, so Linux tries to keep them. And inactive pages are cold, so Linux checks them first. When memory pressure happens, Linux scans the inactive list. If a page was used again, it can move back to active. If not, it becomes a victim for reclaim or swap out. This slide shows the basic flow under memory pressure. When a process needs a new page, it first tries to allocate one. If there is a free page, allocation is simple. But if there is no free page, Linux must reclaim memory. It scans inactive RLU lists, select a victim, and evicts out. Then Linux can get a free page and continue. The important point is, many threads can do this at the same time, so lock overhead can become a problem. Now let's move to swap. Swap uses storage space as memory when DRAM is not enough. For swap out, Linux evicts a victim page to the swap area and changes the page table entry from page table entry to swap entry. For swap in, when the process touches that page again, Linux gets a page for it. Then Linux reads the page from the swap area and restores the entry from swap entry back to page table entry. This slide shows a simple swap flow. During swap out, Linux picks a victim page from the inactive list, updates swap metadata with spin lock, writes the page to SSD, and updates the page table entry to swap entry. During swap in, it sees swap entry on a page for it, finds the swap slot, and updates swap metadata with spin lock, loads the page back to memory, and put it back into the RLU list. So swap is not only I/O, we also touch swap metadata many times. Now let's talk about the first bottleneck. The first bottleneck is lock contention on the RLU list. Linux manages RLU lists per node, and many cores share the same RLU lock. When memory pressure is high, many threads try to reclaim at the same time. So cores spend a lot of time waiting for the RLU lock. This reduces throughput even if the SSDs are fast. The second bottleneck is lock contention on swap metadata. Swap in and swap out both update metadata like the swap map. In Linux, this metadata is protected by a swap metadata lock. So when many cores swap at the same time, the lock becomes very hot. This is one main reason why Linux swap throughput stops scaling. So our goal is to make swap scale well with more cores and more SSDs, especially for all-flash swap arrays. And to do that, our key idea is to avoid a centralized design. Instead, we use a decentralized, core-centric design. We use 3 strategies. First, core-centric swap resource management. Second, opportunistic inter-core swap assistance using delegation. Third, core-affinity page and LRU management. This slide shows the overall structure of ScaleSwap. Swap resources are no longer globally shared. They are owned by individual cores. Each core has its own swap resources, such as swap metadata, swap cache, task queue, and LRU list. Also, each core has a delegator thread. When a core needs help from another core's swap resources, it sends a task to that core's delegator. This way, we reduce global sharing and improve scalability. Here, we compare how Linux and ScaleSwap manage swap resources. In Linux, swap allocation depends on a global view and shared work, so many cores can touch the same swap metadata. But in ScaleSwap, we use a core-centric design. Each core owns its own swap space and metadata. So most swap operations stay local, and we reduce contention. As a result, allocation no longer requires global coordination. A core can allocate directly from its local swap region instead of touching global lists. However, this ownership model raises a question. What if a core's local swap space is full? Or what if we need to access swap metadata owned by another core? To handle this, we use delegation. Instead of touching remote metadata directly, we send a task to the target core's delegator. One important point is the application thread still does the real I/O, so we keep SSD parallelism. Now I'll explain what happens during delegation. For swap out, if local swap space is full, the requester picks a victim page. Then the requester asks another core to handle the swap out metadata work. The delegator updates the swap entry and related metadata, and the requester updates page table entry to swap entry. For swap in, on a page fault, we first check the swap cache. If it's a hit, we read from cache, but if not, we read from the swap space. The requester restores page table entry and puts the page into the local LR list. Then the delegator updates the swap metadata asynchronously. The next design component is core-affinity page and LRU management. In Linux, LRU lists are shared per NUMA node, so many cores contained on the same LRU lock under memory pressure. To minimize this contention, we partition LRU lists by core, removing shared LRU locking. In addition, we modify the page flag layout to store the allocation CPU ID. This ensures that when a page is swapped in or out, it returns to the original core's LRU list. Together, this design minimizes lock contention and improves locality. Now I'll move to evaluation. We evaluate ScaleSwap on a multi-core system equipped with multiple NVMe SSDs to study scalability. We run micro-benchmarks and real-world applications and compare ScaleSwap against Linux Swap, TMO, and ExtMEM. On this slide, I show the micro-benchmark results in terms of throughput and latency. ScaleSwap scales almost linearly as we increase the number of SSDs and cores, while Linux Swap saturates early due to lock contention. Overall, ScaleSwap achieves up to 3.4 times higher throughput compared to Linux swap. In terms of latency, ScaleSwap remains stable without large spikes, even under heavy memory pressure. It achieves up to 11.5 times lower average latency, indicating significantly reduced synchronization overhead. Now, I'll show results from real-world applications. We evaluate 5 memory-intensive workloads, including BFS and DNA visualization. With 8 SSDs, ScaleSwap consistently outperforms Linux swap across all workloads. For example, BFS improved throughput by 2.4 times and DNA visualization by 2.57 times. The other workloads also show consistent improvements. This shows that the benefit extends beyond micro benchmarks to real applications. This slide shows results from Apache Spark. Spark runs many parallel tasks and generates high memory pressure. We use PySpark with the command crawl dataset, which requires terabytes of memory and heavily stresses swap. ScaleSwap reaches about 6.3 gigabytes per sec peak throughput and achieves 1.75 times higher throughput than Linux swap. Here we compare ScaleSwap with TMO and ExtMEM. For TMO, the main issue is CPU overhead. TMO uses compression and decompression, so CPU cost can be high. In contrast, ScaleSwap directly utilizes raw NVMe bandwidth without compression. For ExtMEM, the key limitation is its limited scalability under increasing SSD and thread counts. As the number of SSDs increases, ExtMEM shows little performance improvement and its throughput saturates beyond 32 threads. In contrast, ScaleSwap continues to scale consistency with both additional SSDs and higher thread counts. As a result, in this all-flash setting, ScaleSwap achieves up to 1.64 higher performance than TMO and 5.02 times higher throughput than ExtMEM. To conclude, ScaleSwap is a swap system designed for all-flash swap arrays. We redesign swap to scale with increasing numbers of cores and SSDs. We achieve this through 3 key design choices. First, swap resources are owned by individual cores, eliminating global lock contention. Second, remote metadata access is handled through delegation, preserving scalability without sacrificing parallelism. Third, core-affinity LLU reduces synchronization overhead and improves locality. As a result, ScaleSwap achieves significantly higher throughput and much lower latency than Linux swap, especially under memory pressure. We are pleased to announce that ScaleSwap is now open source. You can access it at the URL on the slide. That concludes my talk. Thank you for your attention.